Chapter 11, Magnetic Material. Today we start new chapter, Magnetic Material. Introduction. We study the different types of magnet. We study the bar magnet. This is the bar magnet. O is the center of magnet. N means North Pole. S means South Pole. This distance L, this distance L. The distance between S and N is 2L. This distance 2L is called magnetic length. Magnetic length plus M is the pole strength of N pole minus M is the pole strength of S pole. Also we discuss the magnetic dipole. The magnetic dipole is nothing but magnetic length. Dipole means two pole, N pole and S pole, and three magnetic dipole moment. The magnetic dipole moment, capital M bar, is equal to 2L into pole strength, that is 2ml. This is the magnetic dipole moment. सर्व आपण अगोदरच्या वर्गामध्ये शिकलेलो आहे पहा की बार मॅग्नेट. हा बार मॅग्नेट आणखी आपण शिकलेलो आहे पहा. दिस इज कॉल्ड एक्सिस ऑफ मॅग्नेट. दिस इज द equator of magnet. The line passing through origin, N pole and S pole is called axis. The line passing through origin and perpendicular to magnet is called equator. Magnetic length, geometric length, magnetic dipole moment, हे सर्व आपण अगोदरच्या वर्गामध्ये शिकलेलो. आणखी आपण शिकलोय when this bar magnet is kept in uniform magnetic field, then there is formation of torque. Today also we discuss the bar magnet is kept in a uniform magnetic field, then how much torque is produced. That is, today we discuss torque acting on a magnetic dipole. Torque acting on a magnetic dipole in a uniform magnetic field. Uniform magnetic field. Now we consider a uniform magnetic field, B bar. This is the uniform magnetic field, B bar, and a magnet or bar magnet is kept in this uniform magnetic field. Suppose this is the N pole, S pole, center of magnet. So this is point C, this is the angle theta, this is the magnetic dipole moment, direction of magnetic dipole moment, direction of force. When the uniform magnetic field B bar and a bar magnet NS is kept in this uniform magnetic field, then the same force acting on two different points at that magnet, this force in one direction and second force in opposite direction, hence this magnet perform the rotational motion, or this magnet is rotate in this magnetic field, and that is we perform or we see the rotational motion in this magnetic field of the magnet. That is, whenever the magnet changes their position, that is the displacement takes place, the work is done. जसा हा मॅग्नेट ह्या मॅग्नेटिक फील्ड मध्ये फिरणार आहे टॉर्क मुळे, इथला फोर्स इकडे वळेल, हा फोर्स इकडे वळेल, हा मॅग्नेट रोटेट होईल, रोटेशनल मोशन तयार होईल, मॅग्नेट असा फिरेल, तो सतत जागा बदलेल, डिस्प्लेसमेंट चेंज झाली, डिस्प्लेसमेंट तिथे तयार होईल, आणि दिस डिस्प्लेसमेंट and due to displacement work is done. Work is done, and this work done stored in the form of potential energy. Due to this magnetic field, the magnet is rotate, and due to rotation displacement is occur and work is done, and that work done stored in the form of energy. Instead of magnetic field, if there is electric field, जर magnetic field च्या ऐवजी electric field असतं तर काय झालं असतं? The work done is stored in the form of electrostatics potential energy. म्हणजे जर मॅग्नेटिक फील्ड असेल तर वर्क स्टोअर इन द फॉर्म ऑफ पोटेन्शियल एनर्जी, आणि जर इलेक्ट्रिक फील्ड असेल तर दिस वर्क डन स्टोअर इन द फॉर्म ऑफ electrostatics potential energy. Now this is the direction of m bar, that is magnetic dipole moment, force, magnetic direction of magnetic field, and this theta is the angle between m bar and b bar. Suppose we consider, suppose this is the point O, this is the direction of torque, this is the direction of magnetic field, this is the direction of m bar, and this is the angle theta. Hence there is formation of torque, and that torque we see this torque is equal to mb sin theta. In previous chapter we discussed about that topic. The torque is tau is equal to mb sin theta, and this angle theta in between M bar and B bar. Now we consider the work done stored in the form of potential energy. Then how much potential energy is produced? The magnetic potential energy, the magnetic potential energy, we say that U M, magnetic potential energy U M is given by UM is equal to 0 to theta 2 into d theta. Therefore, we calculate or using value of 2 UM, that is magnetic potential energy 0 to theta, value of 2 M B sin theta into d theta. Therefore, UM is equal to minus MB cos theta. UM is equal to minus MB sin theta, and this is called the potential energy or magnetic potential energy of a bar magnet. Of a bar magnet. This is the magnetic potential energy of the bar magnet. Now we consider suppose case 1. If theta is equal to 0, that is theta is equal to 0, the direction of M and B is same, that is M bar and B bar parallel to each other, then the value of UM is equal to minus MB cos 0. We know that cos 0 is equal to 1. Therefore, UM is equal to minus MB. This is the minimum potential energy of the magnet. Minimum potential energy of the bar magnet. Now case second, if theta is equal to 90 degree, then the direction of M bar and B bar is perpendicular to each other. Therefore, the value of magnetic potential energy will be minus MB cos 90. Or we know that cos 90 is 0. Therefore, UM is equal to 0. If the direction of this M bar and B bar is perpendicular to each other, then there is no magnetic potential energy. Now, third case. If theta is equal to 180 degree, then the M bar and B bar anti-parallel to each other. M bar and B bar anti-parallel to each other. Then MB cos 180 degree. And we know that cos 180 is equal to minus 1. Therefore, UM is equal to minus MB into minus 1. Therefore, UM is equal to plus MB. This is the maximum potential energy of magnet. This is the maximum potential energy of magnet. That is, if angle between M bar and B bar changes, the magnetic potential energy is also changed. Now, in chapter number 1, that is rotational motion, we see the relation between, or in chapter oscillation, we see the relation between torque, moment of inertia, and angular acceleration. Torque, moment of inertia, and angular acceleration. And this relation is tau is equal to I alpha. But alpha is equal to d square theta upon dt square. This is the angular acceleration. Therefore, tau is equal to I d square theta upon dt square. Compare this torque in previous torque. That is, previous torque is tau is equal to mb sin theta. Then, if we compare these two torque, we get I d square theta upon dt square, which is equal to mb sin theta. But theta is very small. Theta is very small. The value of sin theta and theta is nearly equal to same. That is, sin theta nearly equal to theta. Then instead of sin theta, we can write theta I d square theta upon dt square, which is equal to mb theta. Or this can be written as d square theta upon dt square, which is equal to mb divided by I into theta. Therefore, d square theta upon dt square is equal to mb upon I into d theta. So, equation number 1. This is equation number 1. Also, in previous chapter, that is chapter number in chapter oscillation, that is, we see the equation of simple harmonic motion, and that equation of acceleration, that is d square x upon dt square, is equal to minus omega square x. Now consider only magnitude. D square x upon dt square is equal to omega square x. If we compare, suppose this is equation number 2. If we compare equation 1 and equation 2, the equation 1 is called the acceleration or simple harmonic acceleration of bar magnet. Then the value of omega square is mb upon I, or omega is equal to under root mb upon I. We get the angular acceleration. This angular velocity this angular velocity, using this angular velocity, we calculate the period of bar magnet. The period of bar magnet T is equal to 2 pi upon omega. 2 pi upon values of omega under root mb upon r. Hence, the period of bar magnet T is equal to 2 pi under root I upon mb. This is T is equal to 2 pi under root I upon mb is this equation gives the period of bar magnet, where I means moment of inertia, M means magnetic dipole, B means magnetic field.